500 centimeter cube oxygen was collected over water at 30 degrees Celsius and 752 millimeter mercury pressure. What is the volume of dry oxygen at S.T.P? Given the vapor pressure of water at 30 degrees Celsius to be 32 millimeter mercury. Solution. The question above is a typical question on gas laws, and here we are given the volume of the gas, the temperature and the pressure as well. Hence, we'll be applying the general gas equation, which is also known as the combined gas law. And what does this law say? This law says that for a fixed mass of gas under any set of conditions of volume, pressure and temperature, that is when we are given the volume, the pressure and the temperature, the value of PV over T is said to be a constant. Here I have my PV over T to be a constant K. So now, since you are given a initial volume, pressure and temperature, and we will also be dealing with the final one as well, so here we can have the relationship to be P1 V1 over T1 to be equal to P2 V2 over T2. So the subscript of 1 and 2 here is representing the initial values and the final value respectively. Here we are given the value of the pressure, the volume and the temperature, but the question says we should calculate the volume of the dry oxygen at S.T.P. That is, we are to find the final volume of the gas. If the gas is being collected over water, there will always be a partial volume, or let me say partial amount of water present in the pressure of the gas itself. It could be oxygen, it could be chlorine, regardless of whatever gas it is. But the moment it is being collected over water, there is always a partial amount of water vapor present in the gas, and that's what leads us to the formula we'll be using, which is P total, that is the total pressure of the gas, is equal to the actual pressure of the gas plus that of the water vapor present in it. This is just the first part of the question we'll have to deal with before applying the equation we'll be using. So now we have total pressure of gas to be equal to the pressure of the gas plus the pressure of the water vapor. Here the gas we are dealing with is oxygen gas. So to get the pressure of the gas at S.T.P, we'll have to make P, that is we have to make P subscript gas, that is the pressure of the gas, the subject here. So we have the pressure of the gas to be equal to total pressure of the gas minus the pressure of the water. Same thing as the water vapor present in it. So from this question, we have the total pressure of the gas to be 752 millimeter mercury. That is after which it has been collected over water. The total pressure it's being exerted on it is 752. Meanwhile, water vapor is also present in it. So here now we are being made to understand that the vapor pressure of water at 30 degrees Celsius is 32 millimeter mercury. So to get the actual pressure of the gas itself, we'll be having 752 millimeter mercury minus 32 millimeter mercury. That is total pressure minus that of the water vapor. So here I have pressure of the gas to be equal to 752 millimeter mercury minus 32 millimeter mercury, which is 720 millimeter mercury. So this is the actual pressure of the gas present. Going back to the question, initial pressure of the gas now will be 720 millimeter mercury. The initial volume will be 500 centimeter cube, and the initial temperature will also be 30 degrees Celsius, which we'll be converting to Kelvin later on. So now to know the final volume of the dry oxygen at S.T.P, we'll be making that V2, that is the final volume of the gas. Then our P2 and T2 respectively will be the value at S.T.P, and at S.T.P the temperature of gas is always 0 degrees Celsius and the pressure of gas is 760 millimeter mercury. So the next thing we'll be doing now is to write out the values given, that is to write out our P1, V1, T1, P2, V2 and T2, whereas we have our V2 to be unknown. So let's proceed. So we have P1. We've gotten P1 to be 720 millimeter mercury, that is the actual pressure of the gas. V1, from the question, V1 is 500 centimeter cube. And we have T1 to be 30 degrees Celsius. So this, which will be converting to Kelvin by adding 273. So we have 30 plus 273. Our unit as Kelvin. So this gives us 303 Kelvin. So now for the final values now, P2 at S.T.P, the pressure of a gas is 760 millimeter mercury. So we have P2 to be 760 millimeter mercury. V2 remains unknown, and T2, the final temperature, is 0 degrees Celsius, which is equivalent to 273 Kelvin, that is 0 plus 273. So here V2 remains the unknown, so and to get V2 we'll be making V2 the subject of the formula. I'll be writing the equation again, that is the general gas equation, which is also known as the combined gas equation. So we have P1 V1 over T1 equals P2 V2 over T2. So making V2 the subject, we have V2 to be equal to P1 V1 times T2 divided by P2 times T1. So let's substitute P1 720 millimeter mercury multiplied by V1, which is 500 centimeter cube, multiplied by T2, which is 273 Kelvin, divided by P2, that's 760 millimeter mercury, multiplied by T1, 303 Kelvin. So let's calculate this. Here we have 98280000 over 230280. Our unit centimeter cube, and this gives us 426.78 centimeter cube, which can approximately be equal to 427 centimeter cube. And this serves as the final answer. So going back to the question, so we can say that the volume of dry oxygen at S.T.P is 427 centimeter cube, and that's the final answer.